This is a continuation of our discussion under Chapter 1, the analysis of AC circuit in frequency domain, steady state frequency domain. So last meeting, we discussed about the nodal analysis. So here, we will be discussing about the mesh analysis. So again, the concept behind the mesh analysis, or they also call it the Maxwell's loop method. It's the same concept as what you did in circuits 1 in DC analysis, but this time the only difference again is the type of number that we will be dealing with. We'll be dealing with complex numbers. So let's review the concept. So if we have a simple T network, but instead of resistors, I'll just put here some impedances Z. Let's call it Z1. It can be inductive, it can be capacitive, or it can also be pure resistive. It depends on the problem. Then we will try to apply the concept now of the mesh analysis here. Remember, mesh analysis, the principle behind the mesh analysis is it's based from the Kirchhoff's voltage law. Just like the nodal analysis, it's based from the Kirchhoff's current law. Here, it's also based in the Kirchhoff's voltage law. So this is EA and EP. So if you remember, we first assign our loops or meshes. So here we have two mesh. Let's call this one the first mesh or loop, and this one another loop here. And I will call this one IA, maybe IA, and this is IB. And this is loop A, and this is loop B. Now we want to determine the branch currents. So let's call this one I1, the current passing through Z1, the current passing through Z3, let's call it I3, and the current passing through Z2, let's call it I2. Now, applying the concept of mesh analysis at loop A. First, at loop A. So here we need two equations because we have two loops, IA, loop currents, IA, and loop current IB. So we need two loop current equations. So the first one at loop A, so we have negative IA. You multiply it with the impedances. We can just add the impedances Z1 plus Z3. And there is another current passing through Z3, and that current is IB, and they are in the opposite direction. So it should be the opposite sign of IA. IA is minus, so this should be plus IB, and I need to multiply this with Z3. Then lastly, we have the sign of EA is positive, so this will be plus EA, and that's equal to 0. So this is the concept of mesh analysis. It's based from the Kirchhoff's voltage law. We just apply Kirchhoff's voltage law along the loop. So next, at loop B, we can repeat that again. For IA, in that loop, it's opposite with the direction of IB. So it should be, if IB is negative, let's make IA positive here. So IA, you multiply that with Z3. And for IB, if it's minus IB, then you add the impedances Z2 plus Z3. And the sign for the voltage, because the last sign here will be negative, this is plus minus, so it will become minus EB equals 0. So this is how we do mesh analysis. Now we take an example. Let's try to take the example that we did in the nodal analysis and solve it through mesh analysis. This example here, let's just copy this one and try to solve this one using mesh analysis. So calculate I1, I2, and I3 if Z1 is equal to negative J4, so Z1 is this is negative J4, Z2 is 3 plus J4, and Z3 is just 5 ohms. This one is 100, EA is 100 plus J10, and EB is 100 minus J5. So we don't need the voltage here, we want to solve for the branch currents. But first, we assign our loop currents. So if this is loop 1, or loop A or loop B, let's call it IA and IB. So this is loop A and this is loop B. Then you can apply the mesh analysis at loop A. First at loop A, so we have, what do we have at loop A? Loop A, we can multiply IA with the sum of the impedances, Z1 plus, Z1 is negative G4. You add that with 3 plus G4, so it will become 3. So it should be negative 3. Minus 3 IA. Then there's another current at Z2, 3 plus G4, so we need to add its opposite direction with IA, and that is IB. And that impedance is 3 plus J4 IB. And lastly, for the voltage, it should be positive. Positive 100 plus J10 equals 0. And we can rewrite this, simplify this one, we can put negative 3IA at the other side and also IB at the other side. So it will become positive 3IA. Then that negative 3 plus J4 IB. Then we retain that 100 at the other side, so it's still positive plus J10. And this will be our equation 1. Next, for the next equation at loop B. At loop B. Let's repeat the process. First, for negative IB, what are the impedances along that loop? We have 3 plus G4 and 5. We add them, 3 plus G4 plus 5 is just 8 plus G4. 8 plus G4. Then there's another current passing through this impedance here, 3 plus G4. So we need to multiply that with IA. And it's IB is minus, so it's the opposite sign. So it's plus IA multiplied by 3 plus G4. Then lastly, for the voltage, it should be negative voltage. So it should be minus 100 minus G5 equals, and this is equal to 0. Then we can rearrange. We put IA at the first part. So this will be 3 plus G4 IA. Then we have 8 plus G4 IB. And we can transfer that voltage at the other side, so it will become positive 100 plus J5. And this will be our equation 2. Then we have now two equations and two unknowns. So we can use the Kramer's rule, determinants, to solve for the loop currents. But first, we need to put it into a determinant form. So this will be our determinant form. For the first equation, we have 3IA. Then we have negative 3 plus G4. So we can distribute that negative 3 minus G4. And for the second equation, we have 3 plus G4. Then negative 8, distribute that negative again minus G4. And these are the coefficients of IA. We multiply it with IA and IB. IA and IB. And this should be equal to the constants, or the voltages at the right side of the equation. So the first equation, the constant is 100 plus J10. 100 plus J10. And for the second equation, 100, that should be minus J5. This is minus J5. Minus J5. So this will be our determinant. And we can apply the Kramer's rule. First, to solve for IA, we need delta A, or the cofactor of IA. So I just put it directly here. So we just change the column. This is IA and IB coefficients. The coefficients of IA, if you are solving for IA, change the column for IA, coefficients of IA with the constants. So what are the constants? 100 plus J10 and 100 minus J5. Then we retain, just copy the second column. 3 minus J4 minus 8 minus J4. So that's the numerator. For the denominator, it's the determinant. So you just copy directly 3 and 3 plus J4 and negative 3 minus J4 and minus 8 minus J4. And you're going to solve for the determinants here. So for the first numerator, This is just equal to 100 plus J10. You multiply it with negative 8 minus J4. Then we subtract. That's downward, upward, positive. 100 minus J5. Multiply it with negative 3 minus J4. And that's our numerator. For the denominator, we repeat the process. So this will be 3 times negative 8 minus J4. Then we subtract it. 3 plus J4 multiplied by negative 3 minus J4. Then we simplify this. IA will be equal to, this will be, the numerator will be equal to negative 440 minus J95. Then for the denominator, we have negative 31 plus J12. Negative 31 plus J12. And remember that denominator, that's the determinant. We will be using this again later on for solving for IB. Then calculating again for IA. So the final value for IA will be equal to negative 440 minus J95 divided by negative 31 plus J12. And converting it into polar form, the answer will be 13.54 angle 33.34. 33.34 degrees. So this is IA. And if you look at the figure, IA is actually the same as I1. So we can check if our answer here is correct based from the our calculation using the nodal analysis. So for I1 is also equal to 13.541 angle 33.44. It's the same as our computed value using mesh analysis. Next, for the other loop currents, IB, we repeat the process again, but this time, our numerator, we change the second column because we're solving for IB. So we copy the first one, 3 plus 3 and 3 plus J4. And we change this one with the constant 100 plus J10 and 100 minus J5. Then for the denominator, it's the same. We can just put here negative 31 plus J12. It's the same determinant for IA. Then compute. Then this will be 3 times 100 minus J5 minus 3 plus J4 multiplied by 100 plus J10. All over negative 31 plus J12. Then calculating this one using a calculator, IB will be equal to, this will be equal to 13.44. Then angle 116.3 degrees ampere. So this is now IA and IB. And we can now compute for the branch currents based from this. Again, I1 is just equal to IA. And that is equal to, IA is 13.54. 13.54 angle 33.34 degrees. So this is our IA or I1. Then for I2 will be equal to, where's I2? Or I2 is the current passing through Z2. And there are two currents passing through here. We have IA and IB. So it should be IA minus IB. So this should be IA minus IB. IA is 13.54, angle 33.34 degrees. Then we subtract IB. IB is 13.44 with the angle of 116.3 degrees. So I2 will be equal to 17.87 angle negative 14.94. Negative 14.94 degrees. And lastly, for I3, So where's I3 will be equal to, it's the opposite direction of IB. So it's equal to negative IB. It should be equal to negative IB. And our IB is, so this is negative of 13.44, angle 116.3. So if we take the negative of that, it's the opposite direction. So IB is equal to 13.44 angle negative 63.7. Negative 63.7 degrees up. Or this is I3. I3. So we solve I1, I2, and I3. We can compare our answer with the previous discussion, the nodal analysis. I1 is equal to 13.54, 33.34. So our I1 here is the same. For I2, 17.87, negative 14. 17.87, negative 14 is also correct. And I3 is 13.44, negative 63.7. 13.44, negative 63.7. So our values are the same. We use different methods using a nodal analysis. We also use the mesh analysis. So this is mesh analysis for AC circuits.